we all ready to get started with today's lecture? Yeah? Are we all dead tired? Is it already one of those things, Wednesday midweek? It's a little early for high energy. So hopefully I can get a volunteer to play a game with me. So today we're starting with a game called Heads Up. How many of you have seen this game or heard of this game? Yeah, show of hands. We've heard of Heads Up. Okay, cool. So Heads Up, for those of you who don't know, is a game where, like headbands, where people have on their forehead a name of a celebrity or a concept or a place or a thing, and everyone in the audience has to shout out clues to help them guess what they are without actually saying the words on their headband. So I thought it might be something a little fun, instead of a general recap activity, to try some headband-like or heads-up-like game structure, but with concepts for the course. What do we think? Yeah? Yeah? Could I get anyone who feels like they want to be a guesser? They want to be the person over here who won't know what the word is. No? No? Yeah? Actually, Tim? You up for Tim? Amazing. Can I get a round of applause for Tim, please? All right. Hi, Tim. How's it going?
Good.
Good? All right. So can't look over here. Stand over there. Say hi to everyone around you. I'm going to make sure to pull up our wheel. So Tim, how comfortable do you feel like you've been with the course concept so far?
Well, we're about to find out, I guess.
About to find out? Yeah, okay. Well, let's see. Everyone ready to start giving some clues? Okay, I'm going to full screen this. All right. So, up. Oh. Why? Oh, do I have to? Give me 1 second. Lovely technical issues. Always fun. Okay. There we go. Open. All right, everyone can see that, right? We all recognize some of these concepts up here on the wheel. We've learned these in lecture. We kind of understand what they are. All right, I am going to hand the microphones around. And actually, could I get an assistant today? Would anyone like to volunteer to run some microphones for me? You will still get a Skittle for just taking a microphone to people. Yeah? Amazing. Thank you, Alex. If you wouldn't mind, I'm going to hand you a mic. It's muted right now, so feel free to flip it on. All right, are we ready to get started? Tim, are you ready for us to spin this wheel?
Spin the wheel.
Spin the wheel. Okay. Ooh, okay, so we need to get Tim to guess this word. All right, anyone, start shouting out guesses.
Int.
Int. Yes, okay. Ready? I'm going to count +1. You got 1. All right. Ready to go again? Yeah, maybe shouting works best. I don't think we need a mic. Thank you so much, Alex, but feel free to run. Okay. Ooh, okay.
If.
If.
Else.
Okay.
Else.
Okay, all right, okay, we're getting into it. All right, we run saying statements and structures. What do we got? What do we got? Whoa, okay, we can do it.
This lecture. Algorithms. So you can say anything as long as it's not the word?
You can't say the word, and that's where certain things like foundations of excellent things.
Computing! Oh, whoops.
And I want to say that's a great insight, because one of the big things we cover in this is that idea of thinking about the problem space. What am I allowed to do that kind of works in those peripheral areas? And that's a beautiful version of it. Thank you so much. Okay, ready?
That's good.
Let's go. Wheel. Ooh, oh. All right.
Include.
Main.
You can't say any of the words in the word. So just
Global variable.
Define it after. It's the thing you put before main that you have to define after. If you want this project to be reused, what is that?
Functions.
Before you define it, to show that everyone knows it exists.
Before you define a function.
Ooh.
Declare.
Like a preliminary version of something.
Prototype. Hey, all right. What do you
You're
want?
guessing it.
Declare prototype. Prototype function.
Oh.
Function prototype.
There you go, function prototype. Okay, this is good. We're getting it, and everyone's remembering things. I love this. Okay. Oh no, we did that one already. Oh, is it gonna keep going? Okay, we gotta go. We gotta do one. Let's go again. I wish the wheel got rid of it once we did it. You know? Okay. Okay.
You turn a double into an integer.
Conversion. Type conversion. Casting.
Okay, yes. Do you want to put that word together? What is it? Casting.
Type casting.
Casting. Oh. Tim, you are getting it. You know. Everyone, you've been a really good clues. Okay. All right. Similar, but different.
Block. Function.
Functions. Okay. All right. Thank you so much, Tim. Can we get one more volunteer? Tim, please feel free to take some Skittles.
Thank you.
Would anyone else like to come up to play? Yeah, let's go. Do we want to do a head-to-head? Would you like to come up too, and we'll see who gets it faster from the same clues? It's okay. I'm gonna grab Alex. Can I grab? Yeah. Come on. Thank you so much. Oh, that's true. But the issue is, do you guys remember? Does anyone know how big a human memory is? We're going to talk about memory for computers today. Has anyone heard any heuristics for how much people can remember?
Only a few petabytes.
Oh, petabytes. Well, that's long-term memory, but you haven't been looking at this that long. So it's your short-term memory. Eight words, that's pretty good. The average human memory, we call it the magic number 7. It's a little iffy on whether it's still that, but basically, sorry, I'm gonna hand you a mic. Can I get your name too? I haven't heard. Danny. Lovely to meet you, Danny. And we've talked. Ronald? Yeah. Amazing. Okay. So, Danny, Ronald, how confident do you feel in your understanding of these concepts?
Moderately confident. Very confident.
Very confident, moderately confident? Okay, all right, team. We're trying to make sure they guess it. So, no favorites here. Ready? Oh, just did that one. We'll do like 3 more, and then we'll start getting into today's actual topic. Oh, man. Yeah, do we want to? I feel like I should. If I hide that. Oh, I can. Oh, I'm so silly. This is what I get for not playing around with the game itself earlier. Okay. We haven't done this one yet.
Modular.
Oh, okay. That's pretty close. We're good. Okay. Let's go.
Test.
What do we got? Ooh. You can't use that word.
Imperative language.
Imperative, yes. Okay. What do we got? Ooh.
Character.
That's okay. That's okay. Recall is only one part of games, everyone. Understanding is another one. Oh, we already did this one. Now I know I can hide them. Okay. Don't look back, Danny. Don't cheat.
Try and get a one up on
I know. We're getting fast, but we can't be that fast.
big O.
Oh, already.
Thank you.
Beautiful. Ross coming for your throat. I love it. Okay, one more. And then I think we'll get to it. Ready? One more that we haven't done in case it ends up on something we have. Because like half of the wheel now is things we have.
Okay.
I should have really been hiding these from before, but then you would have known that we only had like 5 left. And that's well within the human memory to know which ones those were. Oh, come on, come on. Ah, nuts.
Nuts.
Ah, beans. I don't know if people still say that. That was like a big thing. Okay, okay. Oh, oh. Okay.
Recursion. Recursion. Oh, while?
Oh, I thought I heard it.
While?
While. Okay, thank you so much, everyone. Big round of applause for Ronald and Danny. Feel free to take some Skittles. All right. Okay, everyone. Are we ready to get started with today? Are we ready to get into it? Are we refreshed and back into thinking about algorithmic concepts? All right. Now I've got to come. All right, we're done with you. If you want to play the game at home with your friends, I'll post the link on Ed. But let's get started. Okay, so last week we left off with this kind of challenge, these disks on top of poles that we wanted to move from one pole all the way to the other poles, when we could only move one disk at a time, and we could only put smaller disks on top of larger disks. And we told you that this was called the Tower of Hanoi or the Tower of Brahma, and it's part of this mythology to it. And so obviously, what I'm going to ask you is, how do we code it? Oh, that's a little mean, isn't it? To kind of just go from, we're playing a game last week to how do I do this right off the top? So let's try something a little more straightforward first that's going to build us up into the idea of how do we actually tackle conceptualizing that Tower of Hanoi problem, abstracting it and its steps, and turning it into an actual piece of code. So how many of you have worked with triangles before? Yeah, we know triangles. We know structures that get built on triangles, aka pyramids of things. Well, we can actually have triangles that as we kind of add more objects to them, we can build up bigger triangles, right? So here, let's imagine we're building this pyramid and we're going through and we're adding blocks, layer by layer, one at a time. So in our first pyramid, we start with one object, one circle, one block. One doesn't really seem like it makes a triangle or a pyramid, but I guess we have to start somewhere, right? So now when we're making our next triangle, we have to add how many? 2. Beautiful. Thanks everyone for the 2s. Love the peace signs going across the lecture hall. And we can keep adding up blocks like this until we get this pyramid that fits this kind of triangular shape, right? But at some point, we want to figure out if I want to build a pyramid that's, I don't know, 10 feet high or something like that. That's not a big pyramid. The pyramids in Egypt are obviously quite large. But, you know, in the classroom here, if I want to build something that's 10 feet high, how many blocks would I need? How many layers would I need to kind of build up if each one of these circles or blocks is a 1-foot block? So let's just intuitively, if I want to build something that's 10 feet high, how many layers would I need if each block itself is 1 foot? Tim, you've already come and volunteered. Anyone else? Let's think. Yeah, sorry, can I get your name? Sorry, I'm just gonna see if somebody can pass back Mike. Danny, can I ask you to see if you can pass that back?
Since they're circles, more than 10 layers, ignoring that, 10 layers.
Ignore that 10 layers. Okay, amazing. All right, if you want to hold on to that, we're going to play a little game called Can We Find the Shortest Path to Whoever's got their hand up with the mics. So feel free to mute that, and then I'll ask you to pass them around. Okay, so if we need 10 layers, how many total blocks are going to go into that? If our T here, we have a subscript with how many layers we got. So T1 has 1 layer, T2 has 2 layers, etc. How do we know how many blocks we need? Can anyone see any kind of patterns that are coming out? Actually, Narcy, can I get you to put it all the way to the back? White polo shirt. And can I get you to remind us your name, please?
My name's Sam.
Sam. Hi, Sam.
The pattern is that it's whatever the subscript is, it's 1 plus 2 plus 3, and then all the way up, adding each integer up to where the subscript is.
So we keep adding each. I did see over here, Elizabeth, did you have another idea? Same one? Okay. Anyone else have any other patterns that they see? I think that's kind of it, right? We see a good set that we can think about every layer as adding a certain number of balls or a certain number of blocks. And because, as Sam was saying, we're adding 1 plus 2 plus 3, that means that every layer we're adding that number of balls to it, right? So the 3rd layer takes 3 balls, 4th layer takes 4 balls. So what would our 10th layer need? Everyone scream out the answer. Our 10th layer would then need how many balls at the bottom? 10. Amazing. Okay. So this is one way we can go about figuring out how many specific blocks we need, is this iterative method where we're going through and we're saying, well, the first layer needs 1, and we're going to add 2, and we're going to add 3, and we're going to add 4, et cetera, et cetera. So let's see if we can code that up and what that looks like. So we're going to go here. Can everyone see my screens up here? We can read that just fine. So like I said last week, I'm not using VS Code. Most of you are likely using VS Code. I have a Windows machine. If you have Windows, you might be using the Windows subsystem for Linux. I am just using a MSys terminal and a text editor here to do some quick coding for you all today. So I'm going to start by making a file. So I'm going to go to my text editor, and I am going to need to have my int main, int argc, char star argv. And we are going to get to what all of these mean later today. What do I need at the bottom of my int main function? Anyone remember? Returns. Okay, for things like that, feel free to shout it out when I'm coding. Otherwise, I'll come by and ask specifically for mics. All right. So I know for this, I'm going to want my program to take in some integer n. That's going to represent the number of layers in my pyramid. Pyramid, if I can spell. Okay. And I'm going to want to print something for the user to tell them how to enter a number for me. How do I do that? We're familiar with this function. Feel free to shout it out. Oh, scanf is to take in the input. How do I print something to the screen? Printf. So you're right. I'm going to need my printf and I'm going to need my scanf. So I'm going to say printf, enter n, and then I'm going to use my scanf. Thank you, everyone, for shouting that one out so I didn't have to ask again. And I'm going to give it %d. And I'm going to tell it to put that in n. Now, wait a second. If I'm using printf and scanf, I need some other statement right at the top here that starts with an include. Remember what I include? Standard input output. Yes. And that will allow us to use these lovely print and scan functions that we've been relying on so far. Okay. And I am going to want to eventually do something where I can just go triangles, iterative, and give it a number, n, and it'll output for me some total number of balls that I have. This is what I want to do. How do I actually make this function? So I need something up at the top, something that Tim guessed for us today. What do I need? Prototypes. So I'm going to say int, because I know that my blocks are whole numbers, right? And so I'm never going to have half of a block that I'm going to use. I'm always going to be using full numbers. So I can use int, and I called it triangles iterative, and it'll take in an integer value.
Is any function that's not main called a prototype?
No, so any function itself is just whatever you call it and then the code. The name of the function itself, we call its function signature, which tells us its type, its name, and what it takes in. The prototype is what we put up at the top of the code, so that way our main function knows that it exists. We talked about last week, and we'll come back to that metaphor today, the idea of calling, that our main function, in order to use any of these other functions, has to call them on the phone. But if they don't know that that person has a phone number, how are they going to call them? That's what the function prototype does. It gives the main function the idea that, hey, you might not know how this works just yet, but trust me, their number is registered. The phone is active. You can call.
Why wouldn't we just define like the whole function?
I'm going to actually ask if, sorry, Sam, can we pass that over? Just because these are excellent questions. And I want to get Tim to repeat them. Tim, can you repeat your first question, please?
So
If I understand correctly, you've just said, okay, we're going to have a function that's called triangles iter.
Yep.
And this is a prototype. So we're just letting main know that we are going to have this function, that it can call that function. My question is, why not also define the function behavior at the same time?
So we can do that. We could, instead of having a prototype, say this, and then put the body of the function there. The reason being is that a lot of times when you're looking at code, you want to make it literate, easy for other people to read. And sometimes if they don't know where the main function is, and I have to scroll all the way down to the bottom of the code to see what you're actually doing and where the logic is, I might forget what's up there. Or even as you're writing code yourself, you might not know what you want yet, or you might have a placeholder idea of this is the step I want, but I don't know how I'm going to do that step yet. And so function prototypes are a little easy way for us to say, I know this step is going to exist. I'll come back to it later. The other thing about it is because eventually as you work through C, you're going to start using header files, kind of like standard input output.h. You might make your own, where instead of doing these prototypes up at the top here, your prototypes will actually be in those header files. So that way you can implement them elsewhere. Does that answer your question?
So it's a little bit analogous to an uninitialized variable declaration.
Very much so. Where here we need int-n to exist before we can have the address, before we can use it in scanf, we need to have the function's name exist before we can call the function. But funnily enough, we don't necessarily need its logic to exist. But for the fun, let's put the body in here since we know it's going to exist, and then we'll try it the other way for later on, just so that we can see that both work. We recommend prototyping because it's good practice. I do want to say that is the official stance of the course. My stance is whatever works, baby. Okay, so what do we want to do if we want our iterative to calculate the number of blocks in our pyramid? What did we say? Sam gave us the suggestion of we're adding up all of the layers numbers. So layer 1 has 1, layer 2 has 2. We add 1 plus 2, then we'll have 3. All right, we got a comment in the back. Can we pass that all the way back, please?
Okay. So you could use a for loop where you count from 1 to the input variable x and add up just like 1 plus 2 plus 3, etc.
Okay, yeah. So we can go through and say, hey, we know that we're iteratively going through, and that means we're going to use a for loop. And that for loop is just going to take from 1 to our layers and add what that number is. Amazing. So let's do that. We're going to go int sum for the sum of all of our layers. And now we're going to write our for loop. So I'll even actually start it with sum equals 0, just so we know that at our base, we're starting with nothing in there. Now, we're going to write our for loop. Our for loop needs 3 things. How do we start? What's the first thing our for loop needs? Oh, I heard it. Can someone say it louder? Int I equals 0. This is our initialization. That initialization means that at the beginning of the for loop, we are guaranteeing that our integer I, which is going to be our counter, is equal to 0. All right, what's the second thing our for loop needs? It needs a condition. That's right. So our condition over here should be that I is less than or equal to X, right? Why would we have I less than equal to X for our for loop? We've already got an answer there. Anyone, why when we're going through iteratively, do we want I to go that way? Yeah, Alex, I'm actually going to give you a second mic. Sorry, I'm getting mic'd a lot today.
We don't want the loop to terminate before it reaches the layer, the final layer.
Exactly. We want the loop to go all the way to the final layer, from 0 all the way up to whatever n actually is, right? And what's the third thing our loop needs? An update. So here, that's where we make sure that we are changing that counter variable so that we inevitably it ends, right? We don't want a loop that goes on forever. Okay. So now we're counting. So what we said is we're adding it all up. So we are going to say that inside our for loop, every time we go through one layer or one step in this process, we are going to add that number of blocks to our sum. And that's how we get sum plus equals I. Make sense? Seems pretty straightforward, right? Is anyone not sure what's going on here? I think you guys have done for loops. You guys have done Python. We were working through this last week. All right. Now there's one last thing our integer function triangles iterative needs. There's one last line here, and that line is related to the fact that our function has a type integer. Kind of like our main function needed something right at the bottom. What are we missing? All right, Alex, I think I should have passed it all the way back up to Elizabeth, please.
You need the return statement to return the sum and not just 0 because you want to use that value from within your main function.
Perfect. So we need to return the sum. Basically that we're saying, hey, as the main function, we're going to call triangles iterative. We're going to tell it to do the math for us. And then it's going to pass back just that final answer. It has no part marks. It keeps none of these intermediate variables that it's created here. It is just going, all right, fine. This is what the sum is. So I am going to now print that out. I'm going to keep a little placeholder variable here just for easy reading that we're going to call sum iterative. This is just going to be where we hold that value from triangles iterative. And now I can say the output of our triangles iterative function is stored in this sum iterative value here. And let's print it out. Ooh, if I can type. Printf, the total number of blocks we need is some integer d, and that is going to be sum iterative. All right. And I'm going to save it. Let's call it triangles.c. And we're ready to run now, right? Okay. So I'm in my terminal. I want to check that this is the right place to find this code. So I'm going to start with ls. And I see up there, okay, I've got my triangles.c. I'm ready to compile. We've all done this now. What do I need to compile? What's our function? What's our call? Clang or GCC. So we're going to use GCC for me, and then we're going to give it our code file. We're going to give it the flag -o for change the output name, and we're going to call it triangles iterative. Just that way we know that this particular output is going to be testing the iterative values. Let's see, will it run? Okay. No errors. Compiler hasn't stopped us. Ready to run it? Triangles, iterative. Okay, enter an n. What do we want? Somebody give me a number. 10. Okay, let's start low. 100. That's a good one. I heard 10. Okay, so I'm going to give it 10, but before I hit enter to run it, what do we know the answer ought to be? So if I start counting, can we all do the sums? 55. Okay, well, let's start with, so 1 plus 2 is 3. 3 plus 3 is 6 plus 4 is 10. 10 plus 5 is 15. I don't know how to do that on my fingers for you. 15. 15 plus 6, I think we're at 21. 21 plus 7 is 28. 28 plus 8, 36. 36 plus, are we at 9? 36 plus 9 is 45. 45 plus 10 is 55. Okay, so we should be getting 55. The total number of blocks we need is 55. So it seems to work right. Okay. All right. So I'm going to hop us back to our PowerPoint real quick because we see that it's working. We see that we're getting there. Now, we realize that we can do this iteratively, but there is another pattern here, right? In fact, what we just did with that counting, that holding that number of what the previous answer was in our heads and just adding that little bit to it, we can have this recursive pattern instead. How many of you have heard the term recursion before? Okay, some of you, not everyone. That's all right. Basically, what recursion is this idea of if we have a step that we know can call itself in a way, that solving this problem requires us adding something to the answer to a smaller version of the same problem, then maybe we can write simpler code that might take up more space, but might be in some ways a little easier to follow. Okay. Now, with that being said, our recurrence relation here looks like this. The idea that we have, well, T2 is not just 3, it's equal to the answer from T1 plus the number for this layer. And T3 is equal to T2 plus some number. So what we can do with this is implement some actual code. So I'm going to do that for you right now. Unless, does someone think, somebody who knows recursion, somebody who's done it before, do you want to coach me on how to do this? Who's done recursion? Yeah? All right. Would you be interested in coaching me? Sure? I was talking to the front, but I don't know. Where's the other voice in the back? In the back there? We'll go with the back now because they're already talking. We'll come to you another time. I'm going to get you a microphone. It's going to come over there. And while that microphone's getting over there, we're going to create our function prototype for recursion here. So I'm going to call it int triangles recursive, and it's still going to also take in some number x. Turn back here. So int triangles recursive is going to take in some integer x, and then we're going to do something. So mic's up.
Yep. Yep.
So can I get your name first before we
My
start?
name is Ron.
Ron. Lovely to meet you, Ron. How would we go about doing something recursive here?
Well, effectively, we need to find a base case that we go back to, and then a recursive case where we call our same function again. In this case, our base case will be x equal to 1, or I guess probably like we'd have some guard cases like if x is less than or equal to 1, we just return 1 because otherwise if we get a wrong input, then it can cause problems.
Can I ask you to speak a little bit louder? I'm having a hard time hearing you.
If we have like x less than or equal to 1 or x equals 1, either would sort of work, but it's better to have that because if we have a 0 input or something, then it'll cause problems otherwise. We just would return 1 there.
Okay, So s less than or equal to 1, we said we'd return them there.
Yep.
What would we be returning with the current
Oh.
condition we have?
Oh yes, sorry. It would be x less than 1 returns 0, and otherwise it would return 1.
Okay.
Yeah.
So we're saying if x is less than 1, we're going to return 0, because that way, if there's no layer to our pyramid, there should be no blocks.
Yep. If x is negative as well, that we just return 0. It's a problem that we don't want to solve.
Amazing. Okay. So now, if else, we'll need our else statement.
Yep.
What do we do next? This idea of this recursive function, this recursive call.
So effectively, we can do we can call our function again. So we can do return x plus the value of the function with x minus 1. So like if we've got
So we're going to return x,
Yep.
which is our current value.
and then we're going to call the function again with x minus 1. So it'll effectively decrease each time we call the function.
Okay.
Yeah.
All right. Yes. So shall we see if that runs? How many people think it's going to run? Okay. How many people don't think it's going to run? How many people aren't too sure? That's okay. Or we're not too sure? That's all right. How many people are still too asleep because it's only almost 11? Okay. Well, let's save, and let's over here create another sum recursive. And we are going to say our sum recursive is equal to triangles recursive of n. So that way we can compare their outputs. We can see if the iterative and the recursive give us the same answer. Okay. So I'm going to copy this print statement. We're going to go sum recursive. And I'm going to do something that I was taught to do this when using print statements as a debugger, is to tell us what exactly we're expecting from this print statement. So this is a little bit of a thing. I'm going to say this is the iterative total. So I'm going to say this is iterative and this is recursive. So I know which kind of print it's coming from and which one I'm expecting to see. All right, so I'm going to save that. And let's go back over here and let me get rid of the new line over there so it reads a little nicer. Okay, so now GCC triangles, and I'm going to call it triangles rec. So we see that it's going to include our recursive function. All right, it's run. Can we see down there? Is that too low on the screen? Do you want me to move it up? Does anyone remember the command we used to get rid of the stuff on our screen? Clear. Okay, so let's run it now. Triangles rec. Let's enter a number. What did we use last time? We used 10, and we knew that that gave us 55. Okay, let's try 10 again. It gave us 55. Okay, shall we try it again? What's a smaller number? What do we know t of 5 would be? 1 plus 2 plus 3 plus 4 plus 5 is 15. All right, so let's run it again and let's see if it'll give us the same one. Okay, it's working. Let's talk about exactly what Ron over there said, this idea of recursion and recurrence and what is actually happening down there. So what is happening is when we start our call, actually, let me go back to the code real quick so you can kind of see that. So here, when we come into triangles recursive, we are first checking, all right, I know my final answer. My last layer is going to have X number of blocks, right? So if my 10th layer is going to have 10 blocks at the bottom, my 9th layer is going to have 9 blocks at the bottom. So I already know that answer as part of the sum. I need to know the smaller problem. Well, what I can do is say, hey, let's make a copy of me. And my second me is going to imagine that I'm only building a 9-step pyramid. And that me goes, hey, if I'm building a 9-layer pyramid, then my last layer has 9. And so instead of counting upwards, 1, 2, 3, 4, 5, 6, 7, 8, 9, basically I'm making copies of going, well, I as the last one know it's 10, and the second one knows it's 9, and this one knows it's 8, all the way down until we get to our base case of 0. There's no one here. Does that make sense? It's kind of the same thing, but instead of going from starting from 0, we're counting up here. We're instead recursing to smaller ideas and smaller problems. And the way that works inside the computer is basically we're going to start creating a stack. How many people have heard the term stack before? Okay, some of you. How many of you have had a stack of pancakes before? Yeah, okay, that's more like it. I'm a pancake person. I like breakfasts. So in a stack of pancakes, we have pancakes one on top of the other. And as I'm making them, the first one goes on the bottom, the next one I make goes on the top. And stacks work the same way. It's a collection of objects that grows as we put things on top of the previous one. So what we're doing inside the computer is making stacked calls and creating a stack frame or creating a stack of function calls, but just to ourselves, to the same function. So during our first call, I've made that first pancake, and I have called at layer 3 here on the slides. I've made my first pancake, and I say, okay, that first pancake we're calling 3, and I'm now been told to make a second pancake. So I know that, okay, my second pancake is going to call for that recursion with 2. It goes on top. Each individual pancake here is one of these boxes that we call a stack frame. It's the individual code, the individual logic inside that pancake. And then I'm going to keep going until I reach the bottom of my numbers, until I've counted all the way down to 0. And then with that, I'm going to start eating from the top down, right? I've made all my pancakes. I've gotten up to my pancake 0 at the bottom or at the top. And I'm going to go, okay, now I'm going to eat it. And every time I eat the pancake, I'm going to do something with its result. I'm going to add its number up. Yeah? Does that pancake metaphor make kind of sense? Okay. All right. So with that idea of a recurrence relation, we can now get back to our idea of the Tower of Hanoi. All right. Can I please get someone up here to help us talk out what exactly is happening in our problem? Can I get a volunteer who'd like to come and play our game? We will grab Alex this time. Alex, if you'd come up to the front. And do we have a microphone close to the front anywhere still? Oh, amazing. Elizabeth, could I get that microphone from you, please? All right. So, Alex, I brought you this idea of the Tower of Hanoi, where we have, in our smaller example, 5 rings to work with here. And what I'm going to ask you to do is to think recursively about this and explain the steps you're going to go about in moving from pole 1. And I'm not going to ask you to go all the way to pole 3. We're just going to have the whole tower on pole 2 today. Okay. Okay. If you wouldn't mind starting and explaining your steps, and maybe we talked about recursion needing base cases. If that's your starting problem, what would you do?
I would take this and I would move it to the second tower.
Amazing. Okay. Our base case is pretty simple, right? And now what if I gave you instead 2?
Well, I would need to move the bottom one to the second tower first. So I would get this here out of the way. I would move this to the second tower, and I would move this back.
Okay. All right. We're all following that so far. That makes sense. I'm going to jump your difficulty for you. Can you move all 5 for me? You did it. You've gotten your base cases. We've followed that, right?
All right.
Can we trust? Okay.
Okay, let's do it. So first you move the first one out of the way. You move the second one out of the way. You get this one. Move that back. You move this back again.
Okay, can I pause you there for 1 sec? That's amazing. You've solved it for step 3. We didn't do step 3. We moved immediately from 2 to 5. How did you know how to do 3?
I just wanted to sort of get everything out of the way, and then I think there's a pattern to everything.
Yeah, it seems like it. Do you want to keep going for us?
Yeah, sure. We move this here. We move this back. Do this. Well, this is not good. Oh no. Yep. Okay. Got it.
Got it?
Move that back. Move this. Move there. That one.
Yep, you're on the right track. You're doing it.
No. Okay.
Think about you solving the 2-disk problem. So
Do that. Move that back. Oh.
can I reset something for you?
Yeah.
So you were a couple steps back.
Yep.
You had this.
This. Yes.
And that looks a lot to all of us like back when you were just moving the 2.
Yes.
Can we restart from there?
Okay.
Yeah.
Just move these. Yeah,
So
sure.
when it was just the 2 disks, how did you solve it with just the 2?
Move this here.
Yeah.
I move this here.
Yeah.
And move this here.
Okay.
And we did it.
Solved it for 4.
First one.
Okay. Amazing. Can we have a round of applause for Alex, please? Okay. Thank you so much. Feel free to grab a Skittle, have a seat. Okay. So that makes sense, right? We watched him do it. And what we kind of broke down there is that recursive process that if we can solve it for 1, if we can solve it for 1, and we can solve it for 2, then 3, sorry, dropping things. Then 3, we can start to make a pattern of going, well, if I solve it for 2, and I move 3, can I use that same pattern of going, well, I'm going to move 2 around again to make 3 happen? And then the same with 4, and then the same with 5. And so in this way, we end up with this recursive element, this recursive pattern. So how do we actually turn that into code? Do we think that we're ready to try that out with some code? Yeah? Okay. So let's make a new file. And I'm going to save it right away as hanoi.c. And I'm going to have my int main, int argc, ** argv. Okay. And I am going to do something we talked about a little last week, which is I'm going to use this preprocessor statement called define. Instead of asking people for an input, I'm going to create a macro that I'm going to call the number of disks in my tower, because it'll just help us if we don't have to, every time we run it, put in an actual number itself. I'm still going to need my include standard IO, caps locked, include standard.io in order to print, but this way we won't be asking people all the time. So I know I want to work recursively. If we remember from the last time, we knew that a recursive call called itself. And really, what we want to do at the end of the day is just be able to call one function, Hanoi, and tell us if I'm moving from pole A, my starting pole, to pole B via pole C. Or the opposite even. We can say 2 from wherever. And I have a certain number of disks. That should just be able to tell me how many steps it takes. That's ideally what I want. I want it to be simple and elegant and easy to read. So let's start by making a function. And we are going to create something called a void function. And I'm going to type out the function names real quick, and then we're going to talk about what void means. All right, how many of you have heard the word void? Okay. So what is void? Well, void is a data type that really means no type. It is kind of like that French idea of staring into the void. There's nothingness, there is darkness, there's nothing there. And we use that in coding to tell us when something shouldn't have a type. So here in our functional element, or at the layer of our function, instead of telling it it should be returning an int, we're going to say it's void. It is returning to us nothing. It is just doing the code we're telling it to do, and we're going from there. So sometimes we are going to hear void functions be called procedures. The reason that is because if they're not returning anything, they're not a function, they're just doing something. But that's a really software engineering term and a really old-timey term. It really doesn't matter. It's just a function that doesn't return anything. As well, sometimes we can have void arguments to our functions. We can have a function that says int func and take in void. And what that would mean is take in nothing. It just means that make sure it has no inputs. I could instead leave it blank, but sometimes memory things can happen that are weird. And so void just declares, I expect nothing in there. And we will talk more about void because it becomes important in later classes and especially later today. So now let's actually use our void Hanoi function. What does it do? So we said a recursive function or a recurrent, oh, thank you for that. So let's use our void Hanoi function. So we know that we need a base case and we need our recursive case. So let's think about what is the base case for our tower? How many rings is our base case? Anyone? What do we choose as our base case? We're going to choose one? Okay. So if n is equal to 1, what are we going to return? How many steps does it take to move one disk over? 1. Okay. Yes.
We haven't declared it.
Oh. We haven't declared n? That is okay. So one of the things we know.
Sorry, that last joke. I didn't see you within the comment.
Oh yes, it's in the. For those of you who can't hear, just to clarify, you might be wondering where is this n coming from? It's coming from the argument to the function. We actually have it declared up here in n. That means that it is not something in our variable itself. It is something that is coming into our function, but we can use it if it has that name. Yes. Sorry, I'll try to get a mic on you. Do we have a mic on the right side? Here. I'm going to pass back. Again, pass that backspace. You didn't have the sharp in front of the group. Oh, I didn't have the hash. Thank you. Thank you. Okay. So we have our base case now. And what do we know about this pattern of solving our recursive case? So let's think about solving 2, right? Our base case is it takes 1 move to solve 1. And so solving 2 is like making 2 moves and then solving 1 again, right? Does that make sense? So I hold it up again. I have 2 on here. Normally, I move 1, solve 1, but here I'm going to move 2 moves, because each one takes 1 move. 1 to move the big one over all the way to the end, and 1 to solve for that smaller one. I feel like we're starting to get a little lost here. Okay. Let's think about it a little more abstractly. Yeah, sorry. Who is the one past that?
So I'm sorry. In your void definition for you have the base case you're returning one, but isn't it a void function so it can't return?
Yes, it doesn't return anything. Thank you. It doesn't return anything. We can still use returns in a void function. We're basically using it to mean exit the code here. It's kind of an ugly statement. In fact, let's instead, no, we're going to use return because if we exited the body, we exited the shell. So it cut our code off completely. Instead, we just want to end this particular iteration of the function. Okay? Getting back to this, recursive case. Okay. Let's think about it this way. I know that my problem has whatever current level it's on, as well as one level below it. And so we're going to follow along with me as I type it, and then I'll explain how it works as we go. Okay? So, okay. So I have here this idea of our recursive case being we call our Hanoi function to move from one pole to another pole via some third pole for the n-1 problem, and then we're going to move it backwards. Why does this happen? Well, in our first case, we just need our one move. In our second case, we need to first move one out of the way to the third pole because we want 2 to end up on the final pole, right? So if 1 has to go to our temporary pole, so that way 2 can go to the final pole, we then need to move 1 from the temporary pole to that final pole. Can I get someone up here to see if they can try that out with their hands to see if it makes sense if somebody who's not me is doing it? No? Can I get someone who feels like they're a tangible learner and needs to hold things in their hands? Are we all, am I wrong to think we're having a moment here or I can conscript someone, but are we getting it is what I'm wondering is, or am I going too slow and y'all are like, we get it, we've done this. No? Okay. Then I'm going to ask for, where is, let's grab someone on the side. Adrithia, are you here? Can I get you up front, please? Thank you. A big round of applause for the person I have voluntold. I really want you to get recursion because it is a concept that is going to come back for you in a variety of ways. And then we will take a break after we get this up and running, okay? Okay. So you're going to start here, and we're going to say we want you here, and this is your temporary pole. So move 1 to your temporary pole. That's our n-1 problem. We've moved it from to where to and via. We want it to go to our temporary, or to our via is our temporary pole here. Okay? Would it help if I renamed that temporary? Do you think via is a little too unclear? Via is unclear? Okay, let's call this temp pole. Okay? So now we've moved it from where it started to the temporary pole via our technically we didn't need the third pole, but in theory via that pole. Now we're going to move number 2. We need to move number 2 to the final pole, right? So that's our current n. That's why it's not here. That's why we're saying move a disk from and then 2. That's our step of moving disk 2. This print statement here is our step of moving disk 2 to the final pole. Make sense? And now we have to go back because our 1 is on that temporary pole still. And so we need 1 to move to our final pole. Does that make sense? What we just did there? Okay. Who has the mic currently? Okay, they're both there. You've already answered. Person beside, sorry, can I get your name? You're being voluntold because you have a mic.
Imad.
Imad?
Yeah.
Okay, Imad, can you then, so we've got 3. Using that same structure, could you please tell Ajiti how to move them? And I'll point out which step in our recursive process we're at.
Okay. First move 1 to the temporary,
Right?
and then move the second one to the other, and then wait, sorry, can you start again? Move 1 to the permanent, move 2 to the temporary, move 1 to the temporary, and then move the last one to the permanent.
Okay, excellent. So we're going to pause there. So remember, recursion counts downwards. So we're starting here with Hanoi at n equals 3. And so we would have recursed to those bases. That's why they moved first. So what you're seeing up here on screen, what would be at the bottom of the stack is making 3 get all the way to that final pole, and solving n equals 2 is what Ahmad asked you to do. That's why we have the 2 stacked nicely on pole B, on our temporary pole. Does that make sense? We're recursing downwards, meaning we're solving the smaller problem. That's why we have something that looks like a solution on our temporary pole as we're working on number 3. Does that make sense? Okay. Thank you so much, Ajiti. Thank you so much, Ahmad. We're good. All right, round of applause for our voluntold. Thank you. Okay. So with this, on our code, I am going to make one simple change. The reason being here, we have if n is equal to 1. We're instead going to have if n is strictly less than 1, because that first move, we want to record it moving over there. We want to record that print statement of it moving. So let's compile and see how it works. Okay, so it gave us some output. It told us for 5 disks how to move. We just walked through how to do 3 disks, so let's recompile it for 3 disks and see if it tells us the right thing. And then I will give you all a break. Okay. Pole A, pole B, pole C. Can everyone read out for me what the first step is? Loudly, everyone. Come on, it's up on screen. A to C. What's the next step? Move a disk from A to B. C to B. What's next? A to C, B to A, B to C, A to C. Okay, so that recursive structure, solving the smaller level and then working up to the bigger one. We see that it works. All right, thank you for keeping with me on that. I know that that was a little hard. Let's take a quick 10-minute break. I know I've held you a little long for that, but when you come back, we will talk a little bit about what that means in terms of the number of steps before moving on to something different. So feel free to take your break. If you have answered a question, please feel free to come up to the front and grab a Skittles. If you have any questions for me, I will be here. Okay, 5 minutes, everyone, or 10 minutes, everyone. Thanks so much. I want to make sure we get this concept. Does anyone have any questions for me about the Tower of Hanoi stuff before we kind of move forward? Tim, yeah. Do you want a mic? Hold on. Just in case everyone has a similar question so they can hear you. Danny, could I ask you to pass that back, please?
During the break, we were trying to step through the function, figuring out how it works. And I guess I got a little confused about how the print statement ever actually happens, because
Yeah.
so let's say it's n equals 3, really simple case. So it's obviously going to skip over the base case because n is still greater than 1, or n is not less than 1.
Yep.
And so we'll go straight through to the recursive case, the first line of which is recurse to Hanoi with swapping the variables around. But the thing is, if it keeps, it will go to n minus 1, so then it will go 2, it will still skip the base case, we'll call again, go down to 1, skip the base case, it will go again until it gets to 0, then it will return. But so I guess, is it, okay, so it's at that point when it skips the line 20, because line 20 will just return nothing and it will skip through to the print statement. Okay.
Exactly. So I'm just going to visualize out here, because exactly what Tim said, the situation here requires remembering that C as an imperative language works step by step. And like we said last week, when a function calls another function, it is going to wait to do for that function's response before it continues. And so what Tim said here was at n equals 3, we have in our original poll 3. And for the first run, it goes through, it skips that if statement, it gets down to a recursive and says, hey, I'm going to call Hanoi and ask it to solve it for 2. And so it's going to take a moment and it's going to pretend like 3 doesn't exist and that the problem it has is 2. And now 2 is going to run, and 2 is going to skip that if statement, get to that first recursion and go, whoa, okay, I'm going to call up 1 and say, how do I solve that? It's going to pretend 2 doesn't exist. 1 is going to go, skip that if statement, and go, I'm going to call 0. And 0 is going to go, you do nothing, and hang up. And 1 is going to go, okay, cool, I did nothing, I hung up. That's that first recursion. And now I'm going to hit that print statement. So 1 is now going to print, okay, move me from here to, remember that temp pole is our 2 up at the top, to the temporary pole via the third pole. The via is really just to allow for that second recursion for later on. So we'll get to that. So now 1 has solved itself. It says, I am here from pole 1 to the temporary pole. 1's going to call 2. And remember, now 2 looks like this. 2 thinks it's on the first pole, and 1 is on the second pole. And 2 is going to go now to that print statement and say, I'm going to go to the last pole. And now it's going to hit that second recursion, where it's going to call 1 again and go, hey, you're not on this last pole with me. How do I solve moving you over here? And 1 is going to start again, and 1 is going to call 0, and 0 is going to go, you don't do anything, hang up. 1 is going to go, okay, now that I don't do anything with 0, I'm going to move from my temporary pole to the final pole. That's that second recursion. From the temporary pole to the final pole, that's the 2. And now 2 is done. And so it calls up 3 and says, hey, we figured out how to get us over here. Or technically it would be over here. And now 3 goes, okay, cool. So I can now move to my print statement and then call 2 and go, hey, 2, how do I get you over here to me? And then 2 calls 1 and it does the whole song and dance again. So that was the visual representation of what Tim just said. And that's why it's important to understand that idea of the stack, what is happening when in the recursion, and that concept of functions calling each other imperatively, because that waiting to get that response is why we have the double recursion in that print statement there, is because we have to wait to know what to do with our current case.
So I think the reason it's confusing is because we're used to thinking of problems chronologically, So when we're actually, like when you call people to actually solve the problem, they have to do it chronologically. They don't have the freedom to, get in the time machine to the future where they've already solved it and then rewind backwards. But that's exactly what the computer's doing. It's pretending that it's already solved it and then working backwards chronologically from the solved state to the beginning.
Exactly. The computer is going, I am going to know the future. I'm going to know that solution. Excellent. And thank you for that insight. That is really, really helpful for us. Okay. I am not going to hold us up on this anymore. I am going to take a minute to talk about what is the runtime of this. How many steps do we generally need to solve this? And the answer is based on that recursion, right? How many steps is based on how many times do we have to solve that subproblem? So I'm going to explain to you what's happening here. This is not a formal proof of its runtime element. This is just conceptual. Since that's the thing that's happening the most, we have to remember how to calculate that. And in calculating that, we realize every time we solve it, we're having a tn-1 problem that we're solving. That's that recursion. We're solving the runtime of the smaller step or the smaller problem. We're adding our print statement. That's one step. And then we're running that recursion again on that smaller problem again. And so in that way, we know solving any of our problems is going to involve 2 times the number of steps for the subproblems plus 1 for that final move over to the disk. And so the way that this ends up working in terms of seeing how many total steps it will take, and therefore the runtime, is by figuring out what the kind of pattern is in those final solutions. So most of you are used to patterns from when you started doing algebra and math and thinking about series and sequences. Even before that, you might have done stem and leaf plots where you kind of have numbers and you're trying to see what the difference is between them. And so when we solve out for t to 3 here, we can see the number of steps is growing. So with that kind of back substitution of seeing what the answer is, and these finals, can we think of any function that describes this pattern? What do we see here is the relationship between n, our number in the brackets, and our solution? Yeah, in the brown shirt, please. Can I get your name too?
Yeah, my name is Atar, and it is like 2 raised to n minus 1, the whole minus 1.
2 to the n minus 1. That's right. So we take whatever our number is, n. When we square it, 2 times 2 is 4, minus 1 is 3. 2 times 3, 2 to the power of 3 is 8, minus 1 is 7. And so in this way, that's the number of steps we're generally going to see. We can also visualize this as back substitution if this helps anyone, where you're putting in what the full equation is instead of just the answer of T1, T2, whatever. And in doing this, we end up seeing that any solution is pretty much the sum of 2 to the power of n. Did I have a question back there? Anyone have a question? That's okay. So we're not going to go over this, but this is just basically to know that since we have this pattern of the number of steps is the sum of 2 to the power of n, and that the sum of 2 to the power of n comes out to, when you have a finite number, 2 to the n minus 1. And that means that our runtime, our worst case analysis of the runtime, is that it's going to take 2 to the n time. If each step takes 1 second, that's going to be 2 to the n seconds. The reason we drop that minus 1 is because worst case runtimes only care about the biggest value there. And 2 to the n grows way faster than 1. 1 doesn't grow. 1 is just a constant. And so with big O notation, we drop the constants. So with that, we're going to move on to a different concept. We're going to need a volunteer to help me with some chemistry. I know I've asked a lot of you all so far, but who feels like they are a bit of a potions master? Because I have 2 concoctions here, and I need to figure out how to swap them between bottles. Yeah, coming up, round of applause. Okay, So here we have our red potion, and I'm giving you a fun little label. We'll call it X. And we've got a potion here, Y. And I want to swap their bottles. I want to put X in Y and Y in X. If I give you a mic, how could we do this? It's okay if we need something.
Easiest way is we have another container.
Another container. So if I give you this container and call it Z, could you show me how we'd swap that? All right. While you're thinking about that, I am going to go through and start kind of coding up the process for it to get an idea of what exactly we're going to be doing. Ooh. Okay. So we had X to Z. So we had int X, Y, Z. Let's say X is equal to 5, Y is equal to 10, and we don't have Z. And we put Z equals to X.
Now we put Y into X.
Now we put Y into X.
And finally we put Z to Y.
Z to Y, okay. So, big round of applause. Thank you so much. Yeah, finish that up. So before the swaps, we're going to have X is equal to some character or some number. Y is equal to some number. And X and Y. And then after this swap, yeah, we're going to print the same thing and see if it holds. All right, how many people think this is going to work? Hands up, gonna work? Yeah? I think this is gonna work. This seems good. Swap.c. Okay, so let's try it out. How many people think it's not gonna work? How many people aren't sure? Okay, some people think it's not gonna work. Some people aren't sure, okay? So swap.c. Okay, it compiles. Let's run it. Okay, so it seems to work. Before the swap, X is 5 and 10, which is what we said originally. And after the swap, X is 10 and Y is 5. Seems great. Let's turn it into a function because that's a lot going on there. What if we want to keep swapping them back and forth all the time? All right, how do I write a function? Well, I need that prototype that we talked about. And this one is going to also be a void because we don't need to return a number. We're just changing them, right? And I'm going to call them int X and int Y. So that way we can keep track of which ones we're putting where. So in our function, swap, we're just going to copy and paste everything we have up here, right? We need to have some variable Z. We don't output it, so we'll put it inside our swap function. And we're just going to take this. Okay. Int Z. Z will go, X will go into Z. Y will go into X. Y will go into Z. And now we're going to do that thing that functions do. We're going to call swap and give it X and Y and tell it to swap there. So that's perfect. Everything should be the same. All right, let's compile that bad boy again and run it. Okay. Wait a second. That didn't work. Crud. Okay. Why didn't that work? Well, in order to understand that, we need to understand something about C. that in functions in C passes by value. What that means is instead of giving the function the actual x and y's, we gave it a picture of x and y. Basically, we gave it a photocopy of x and y and said, hey, function, work on these little photocopies here. And it did, okay, cool. And it swapped the photocopies, but that didn't tell us anything. The photocopies aren't the real variables. We need to work with these real variables, right? So let's go back to the code and see if swapping's actually happening inside the swap statement. So I'm going to take those same print lines and put them here inside my swap code. And I am going to say, this is coming from swap, and this is coming from main. Okay, so we see here that swap is doing something, but it's just not hitting those original variables. And because of that, we need to talk about something called scopes. So the scope of something is basically telling me what we can see or hear, and therefore what we can work on in our program or in our functions. So can anyone think of a scope that they're used to in real life? I'll give you an example of one right now. I am someone you can all see and hear. Inside this room, you can all see and hear me. But do we think people across the street can see or hear me? Yes? No? No, I see some head shakes. I might be loud, but I don't think I'm that loud. Okay, can anyone else think of a scope in real life? Something that is a limitation to what you see or hear and can work with. Come on, anyone, yell one out.
What do you can't spend the Australian dollar in Europe?
The cost of the Australian dollar in Europe, money anywhere, right? Can't use my Australian dollars outside of Australia. I have to do some kind of conversion first. I heard another one over here. Any ideas of a different kind of scope? Something that, what? Jurisdiction, what I'm able to legally enforce upon. So there are all these examples in real life of things that have limited scope. So the first thing, and the reason why our variables didn't swap properly, is because we're working in something called local scope. Local scope is the idea that a function maintains its own memory, maintains its own copies of variables and things, and that those don't escape that function. If you remember last week, I said when a function is calling back to the main with that result, she throws away all of her work. She doesn't need to know any of the process. I'm just giving you the result. That's exactly what's happening here. Inside the local scope, I might be using things, I might be doing things, but they stay in my area. No one outside knows about it. Okay. So with that though, if we come back to our swaps example, we see that happening here. The x and y that we're passing in exist inside this new scope of x, y, z, but not out here. We can't call z out here. We have an undefined z variable here. It doesn't do anything, so we can even get rid of it. And what this allows us to do is to reuse names sometimes, because here we have our int x and y that we're passing into swap, and we reuse the labels x and y down here, even though they're not the same x and y. In fact, we could swap these labels and it would still work exactly the same, even though the first one is now called y and the second one is now called x. Or even if it's called r and q, it doesn't matter, because inside the scope of this, all that matters is whether the variables exist in that scope. Make sense? We get that? Okay. So the next idea related to local scope is this concept of code block scope. This is where inside those curly braces of code in C, that has its own memory, that has its own concept of what it can work on. So I'm going to go back really quick to a previous example we did earlier today, our triangles example. And in our triangles example, you might remember that I had this for loop here where I went int I is equal to 0. This is an example of code block scope. What that means is if I decide in my triangles iterative to try to print I out here, it shouldn't work. In theory, it shouldn't work, but to be honest, sometimes GCC will do things that I don't always expect. So GCC triangles.c. And I got this error that I have an undeclared I in my print statement because this I only exists inside of that for loop. Does that make sense? So sometimes you'll have seen Dr. Connie go int I out here and then just set I equal to 0 in that loop there. And what that means is now we can access I as part of the larger function because it's not just limited to that for loop. Okay, cool. We're getting this. Can I get some thumbs? Or this is simple. We're getting this. Okay. All right. So the last scope to think about is global scope. This is where you can be seen by everyone. It is constant. You can be visible to all the functions. You can be aware of everything going on. Now, how can we do that in our previous one? Well, let's go back to our swap example. What if instead of having int x and y here in main, we take them out and put them here above main? Could that work? Our global scope is set outside of our main function, which is our entry point to our C code. And not a lot can happen in that global scope. However, we can actually set some variables because it doesn't take that much processing power to do. And so now here, if we have our scope of x and y in global, our swap should work because the swap function itself can also see that global scope. All right, ready to try it? What happened?
I think you might have messed up the
variables? Oh, I may have, yes. All right, let's switch them back to x and y for my sanity. Okay, so if z is equal to x, then x is equal to y, and y is equal to z. All right, let's try that again. What did I do here? Oh, actually, this is perfect. This leads to something that I wanted to talk about, the concept of shadowing variables. So the reason why it's not working the way I intended to is because I've called x and y inside swap, x and y, but I also have x and y up here in the global. And local scope is kind of the highest precedence in scope. And so what that means is that the x and y I have in local, in the function, is what's being outputted and what's being worked on. So if I instead change these over here to R and Q, and I swap R and Q, so that way the names aren't being messed up, then I should have a working swap. What did I do here? Ah, the prints. And this is why compiler errors are helpful, because even me up here coding will get it wrong and make silly mistakes. Okay. What am I doing wrong here? So instead of troubleshooting that there, let's talk about what we can do in terms of, whoops, sorry about that. Things are going wrong today, but that's okay. Sometimes it happens. Okay, so we recall from last week that when a function calls another function, it passes in the variables and it does work on those variables and then throws them out and calls back to the main function with an answer, that output. And in theory, our global variables should be able to be affected by this. But we don't usually like global variables. The reason we don't usually like global variables is because it can get messy. There's a lot of things happening at the top of a global variable that makes it susceptible to other kind of rewriting or functional issues, etc. And so instead, what are some things we might want to do if we want our function to have memory? If we want our function to say, I remember how many times you called me already. Well, we can do something called including a static variable. So a static variable is a variable that still exists inside the scope of a function. So it's still part of a local scope. However, it retains its memory and it retains its value between iterations of the function. So if we come back here, we can declare a static variable by putting the keyword static in front of the variable name itself. And so here, I will print out the number of times we try to call swap, even if swap does not happen. Now I'm going to, for now, comment out this code because we're just talking about statics. And let's call swap a couple of times, just so you can see how that works. Okay, something seriously weird is going on, and I don't know why. Because all of this ran yesterday when I was testing this for you. So let's take a minute and take a 5-minute break while I figure out what is going on. So please use this time, grab a drink or something, and I'll figure out what's going on and get back to you all. So if we roll back here, so the issue with the global variables, I think, comes back to the aliasing, that we are shadowing these global variables inside the actual functions. And so that's why X and Y output's weird. Okay, moment of truth, fingers crossed that my static variable works properly. Okay, Drum roll. Can I get a drum roll? Okay. We're looking for the n to increase. Okay. So the number of times it's being swapped. 1, 2, 3, 4. It's increasing. So the reason that that's happening is that static keyword, that we are able to have this local variable retain its value instead of being thrown out completely. Make sense? Okay.
Effectively, it only reads line 31 once. It's not reinitializing it every time you call it.
Effectively, yes, exactly. All right. So the moral of the story with scopes is that they can be tricky. They can be the reason why sometimes your code doesn't work, and they might be what is going wrong properly. So the issue here is we want to be able to actually swap these variables. We don't want to have it in one function. We don't want to have whatever's going on here with my global variables. We want to be able to go, hey, I take this, and I take this, and I swap them. Can anyone think of an easier way to do that? If we have this analogy here of variables as labels on the bottles, wouldn't it be a little easier if we could just take the variable name and go, you get that one instead, and you get this one instead? Wouldn't it be nice if we could do something like that? We do have a way to do that, and it involves memory. Now, this is the point where I was going to give you another quick break, but since we just got back, can I get a show of hands? How many people need 5 more minutes? How many people are like, I need 5 more minutes to do things? Okay, a couple. Let's take 5 minutes, be back here at 12:10, and we'll talk a little bit about memory. Welcome back, everyone. We're going to talk about something a little different. And I'm going to introduce you to a TV show that I used to watch as a kid. Okay, that was a little funny and campy and silly, right? So that's the show called Reboot. It's Canadian content from back in the 90s. It's one of the first ever fully 3D animated TV shows, where basically it asks the question, what goes on inside the computer? What is actually happening inside our computer that we're all using every day? And it follows the adventures of Bob, who's a guardian, Dot, and all of these people-looking people, or they call sprites, who represent programs inside the system or processes that are running inside the system, as well as things like viruses as other programs inside the system. And it's interesting because they all live in a place called mainframe, which is basically a computer that at the center of it is their central processing unit, like a city hall, and around it are all of these neighborhoods of things that are memory, effectively. And I didn't realize until I was doing software engineering and learning more about computer hardware and architectures that actually this is a pretty good visualization of virtual memory and what's happening when you think about what is going on inside your computer, where variables are stored, where information works. So generally, in our virtual memory, we actually have a stack of memory here that is allocated for our programs, where you can see in this blue the stack. It's a little weird. It stacks in this way, count down. It addresses a certain type of memory and then counts down until you get towards the heap, which is lower memory, and a bunch of other different types of memory reserved for any individual program. And that maps pretty clearly to neighborhoods, right? We have our different little sectors that have different zoning laws and different reasons for why we're there. And even though this is really stylized, it also maintains certain properties that are true about memory. So one is that it's contiguous, meaning that it's all connected. So all of the addresses go in order, even though they're segmented for different things. In the same way that neighborhoods inside this computer town are connected to each other, even though they're not exactly in the same area code or not exactly the same. And that this memory is based on functions, right? They're doing different things. There's a park area and a business neighborhood and the place where all of the people live. All of that is different. So we're going to kind of use this metaphor of the computer as a town or the computer and mainframe as a city to talk a little bit about memory today. So we can think about data as little people, our ones and zeros, our binomes. This is the information that we're storing, right? Every time we create a variable, we have data in it. And all of that data needs somewhere to live. We need apartments, we need houses, we need locations that we can actually build for them to live. How do we find that? Well, if these locations are all in a contiguous block, we can think about it as houses on a street or apartments in a complex beside each other. And the operating system, or in our case, dot, our command.com, as she tells you in the opening at one point, tells everyone by looking at the map and going, okay, we have space over here for you to build a house. You have new data, we have this neighborhood, we can put it over there. All of the variables that we're creating inside of our functions, inside of our programs, go into the neighborhood of the stack. The stack, like I said, starts with a certain address. This is the beginning of our neighborhood. And it starts at the level of high memory, so one of the highest addresses you can start with. And unlike before, where we built upwards, this one's building down. It's a little different, a little weird, but it means that our housing starts at a high address, and we build out as new data gets a house to a lower address. So with that in mind, I'm gonna need some help from a couple of people to demo some things. Could I get 2 volunteers, please? And our volunteers, our lovely volunteers, are going to be tradies for us today because we are going to be building some houses. Yeah, okay, 1, 2. Can I get some round of applause for our tradies? All right, pick one, put them on. Let us know that you are a tradie. You are building for us new houses for our data to live in, and I'm going to grab some things to give you. Can we grab the... Oh. Amazing, thank you. Yeah, I need both of them. Okay, so we're going to use mailboxes here as our analogies for our houses, where our data is going to live. Okay, amazing. So can one of you grab, who's going to be our first tradie for the day? Who's going to be our foreman? We'll put you as 1, and we'll put you as 2. Okay, so we said here that we are going to be building these addresses. So every time I write a variable, I am going to be creating somewhere for that to be. And I am going to be giving it an address. So really quickly, an address is just a number that designates where in this memory the building is going to be. Because of the fact that addresses are dependent, or the length of them is dependent on the operating system size, they get really long, and so we represent them as hexadecimals, right? So here, if we had a 32-bit operating system, that's 4 bytes of memory, or 4 bytes long of the number, so it gets big. In a 64-bit system, it'd be 8 bytes long. That's a long integer. That's a long number. So hexadecimals, for those of you who haven't seen them, are often described with a little 0 in front of them and an X to indicate it's a hexadecimal number when you see it. Hexadecimals also, for those of you who don't know, use the digits from 0 to 9, and instead of wrapping around again, it then uses the letters A to F. So you'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then you'd go 1, 0, 2, 1, 2, 1, 1, 2, 1, 3, blah, 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 until 1F, and then you'd go to 2, 0. So for our tradies, we're going to start building a place. And we know from our stack that the numbers start at the higher address and work down. So I'm going to grab our first tradie here. So you're going to build our first house for today. And I'm going to ask, in hexadecimal, which of these are higher? This one's higher. Agree? Yeah? Thumbs up?
Letters are always higher than numbers.
Letters are always higher than numbers. Excellent memory for that. Okay. So I'm going to give you this, and we're going to tape it to the side of your mailbox because that is your house, or that is the house you have built. All right. If I can find where the tape starts. Today is really a day of misfortune. Can't even get the tape to work. Amazing. All right. So here's our house. There's nothing in it right now, but data can live there. And now we're going to make another variable. And so we're going to get another house. And so now we're going to start by putting the address on you, and I'm going to explain how far away these houses should be. Let's stay there. We can all see that, right? So the houses are going to be spaced apart, these addresses, based on how big the memory of the data type we need is. So if we remember all the way back to lectures 2 and lectures 1, we said that our data types have different sizes, right? Characters can take up to 256 values. That's 2 to the 16. Integers can take up 2 to the, what is it? 2 to the 32. Doubles take up 2 to the 64. So if I am making a character here, I need my mailboxes to be far enough apart that a character has space to live in their house. Does that make sense? The house needs to be big enough for the people living inside of it. So let's go with characters for now, which are going to be 4. And so can I get you to start from him and walk out 4 spaces? 1, 2, 3, 4. Okay, cool. Let's walk a little bit back there just so that we're not on top of each other. Okay, so we have this idea of characters in houses as memory, right? And the locations are spaced apart based on the data. And in each house, one thing lives, one piece of data lives. So in this show that we watch, we have our villain, our virus, Megabyte. If we know that viruses, like everything, are some kind of program, have some kind of data attached with them, he must live in a house somewhere. So how can we find Megabyte? How would you find someone in the real world if you were looking for them? Feel free to shout it out at this point.
House by house.
We're going house by house knocking? Dang, yes, we could do that. We could go to every single door. But what if I have like 20 houses? I have 2 here. God, what if I had like 1,000 houses? Yell it out, guys. What would you do? Phone book, yellow pages. We would need something to be able to find out where this person lives. We are going to track them down. Okay, can I get someone to be our guardian in training today? Would someone be willing? Yeah, come on down. All right, so in this show, guardians go around doing stuff like this. And they have a special ability, which we kind of have as programmers, which is they have something called a key tool. So I'm sorry for this low budget cosplay, but I'm going to ask you to put that on as a wrist guard because it sits there. And unfortunately, I'm going to ask you to hold this on top of it as your command tool.
Yep.
So our guardians will often access their command tools in the same way that we as programmers will. We have to put in some kind of command, some kind of input. And the way that they do this in the show is by saying glitch, which is the name of his command. For us, it's C, and then telling it what to do. And specifically, if we're looking for an address, Bob, what would we use? Ampersand. So can I get everyone to say glitch, ampersand? Ampersand! Everyone loud, come on! Ampersand, slap it, do it, boom. And then we would have, if this was our 3D TV show, woo, the ampersand command comes down. So what does the ampersand do? It's a low budget cosplay. Things are not going well today. It's fine. So addresses actually allow you to see, or the ampersand actually allows you to see the address of the object, which basically means we can figure out which house someone's in. So, all right, we need the address of Megabyte. Can we say Glitch, address of megabyte.
Glitch, address of megabyte.
Hell yeah. I mean, heck yeah, I need to cut that out of the video. But you would get, woo, boom, a piece of information. The ampersand address, I'm here. I'm gonna try, man. It's been a day. I'll hold this for you. So it gives you somewhere to check. All right. With this, we can now go and try to find this house. All right? I'm going to go back and try to hang out here, everyone, for a minute. I'm going to try once again to poorly live code something for you. This didn't work earlier, but maybe today. So let's say that we have, I really should like store this in a little file somewhere so I'm not constantly typing this out. Okay, so we said we have our characters because they're characters in a TV show, so why not? And we'll call him Megabyte because he's Megabyte, and we'll represent him with an M for Mega. Okay, and we have our character Bob, who is our guardian, and we'll call him B. And let's have our character Dot because why the heck not? And we'll call her D. All right, so these characters are stored somewhere in memory. Let's start by figuring out where. Well, we said we could use our ampersand. So Megabyte's address is, and I'm going to introduce you to a new format specifier, %P. That is the format specifier for an address, or what we will discuss lately, a pointer. And we are going to use our ampersand command and Megabyte and save it as a file, reboot.c, and see if that runs. Yes, I'm in Reboot. Okay, cool. GCC, Reboot. Reboot. Okay. So it tells us where Megabyte lives. We can also see all of those things we talked about, that if we instead printf Megabyte's size, size of Megabyte, we can see that he is a character that would be 4 bytes long. Not so mega, honestly. It's fine. This is a show from the 90s, back in the era when people thought you would only need 64 megabytes ever for things, and megabytes were big. So 1 byte is how big Megabyte is bytes. 1 byte is the length of a character, which is that 16 bits. No, sorry. 1 byte is 8 bits. There we go. Thank you. Okay. What did I do here? Yeah. Okay. Cool beans. So that's how addresses work. So now that we have an address and we can know where something lives, we actually need to figure out how to get there, right? What is a way that in the real world, we know his house, this is where he lives in the show. What's a way we would get somewhere if we have the address?
Drive by car.
Drive by car. How would we know the directions to get there?
Google Maps.
Google Maps, GPS. We have some other function, some other command that is telling us how to get there. And we actually also have that in C as well. Now, what we do for that is use something called pointers. So pointers are the name we give to a specific type of variable that tells us an address. So it gives us those directions about where to go and where something lives. And in particular, we would, for our demo here today, basically say glitch point.
Glitch point.
Boom. And hold on to that for me. Whoa. We'll walk a little closer. What address did we give you? 06B? All right, we're gonna walk. So glitch, because it does not have infinite, but that's a limitation of the real world. Can I ask you to hold that for me? Basically goes, I know where that is, and tells our heroes where to go. So how do we do this in code? Well, basically, we create a new variable that's called a pointer variable. And what we're going to do with it is we have to give it a type so it knows what type of data it's looking for at some point. So for us, that would be our character type in this case. And then we use this star value to indicate that it is a pointer to the operating system, to the compiler. So if we go here, we can create a car star that we call megabytes address, and that is now a pointer. But it's not a pointer that's initialized. It doesn't tell us where it's looking. And this is where the ampersand works with it. By telling us that it is going to be pointing to megabytes address with that ampersand. That makes sense so far? Okay. Cool beans. Fun facts about pointers. Pointers are all equal size. They are considered 1 byte long. And they become really efficient, therefore, for finding things, because otherwise we would have to be constantly repeating or storing memory over and over again. Instead, we have things there. Yes, Tim, do you have a question? Yeah. Let me actually get you a mic since it's like a question. Thank you.
So there's a lot of memory in the computer.
Yes.
And so there's I guess if we're talking just about this program, there's a smaller amount of memory that's allocated, but the address would still have to be like.
It's taking up some memory. Yeah.
Right. I guess my question is, how can every pointer be a byte if a byte, as you said, is only 8 bits, and so therefore it cannot, like, it has a limited number of things it could point to. How does that, like, if there's so much memory, how can a 1 byte pointer tell you where to go?
So the reason that the pointers are small is because their fix is just that hexadecimal number. And because all they are is really the direction. Think of it as like what's in the pointer is an arrow, right? And so because of that, it's...
It doesn't store the full memory address.
So it stores the address, but not what's at the address, right? It's just kind of like, here is the direction. You got to go figure out what's there. And so because of that, it is smaller than the thing that it's trying to store, except they're as big as, I think technically they're not 1 byte. I believe they're 4 bytes. They're the size of a character, or they're the size of the length of an address, what it can be.
So to be clear, every single piece of memory on your computer can be specified in 4 bytes.
On a 32-bit system. Yeah.
Okay.
On a 64-bit system, it's 8, but it's that length of how long can it store addresses, how many houses can we build in this space. But all pointers are the same side regardless of what type they are. So that distance between them was based on who lives in the house, but the size of the actual address is determined by the operating system, right? That's how many total numbers it can have. And so even though they might be further apart, if that's a character and let's say over here is an integer, they might be further apart because of the space that needs. The actual numbers on the house are going to be the same length. Does that make sense? Yeah? Okay. So we now have a pointer to an address, and we can see that this works exactly the same as just getting the address itself. So if instead of saying I am looking for and then the ampersand megabyte, I can just say megabytes address, save it, recompile, and it gives us the same number here down at the bottom. I'll clear it just so it's a little higher up and easier to see. So same number. So the address is stored in the pointer. It can be referenced in that way. This is going to become really, really helpful later on when we are doing certain data structure things and generic information. Now, here's a question. Right now, we have taken megabyte's address and told it megabyte lives here at this house already. So we've initialized that pointer from the get-go. Well, like you said, there's a lot of memory in a computer, and it's physical, really. It doesn't go anywhere, right? Like that memory doesn't stop existing. So in theory, I should have a pointer that can also give me Bob's address. But what happens if I don't initialize it? I don't tell it where to look for Bob. Has anyone tried playing around with uninitialized variables in their code before? Yeah, it can create some wonky things because the reason being is there's always something there. It's just not necessarily the thing you'd expect. So if instead we said, hey, show us what's at Bob's address, we know if I put here instead Bob's address for the address of Bob. Nope, wrong one. This one. It's going to give me something completely random. As you can see here, Megabyte's address is initialized, so it matches. Bob's address by the ampersand is this, but the pointer is pointing somewhere completely gosh darn different. So what can we do? What if, for example, we're working in code where we don't yet know where Bob's address is? We don't know at the start of it when we're initializing this where it's going to be pointing to. Well, we can use something called nulls. How many people have heard the null word? Nulls do exist in the TV show, by the way. They are these little gremlin things. It's what happens when you destroy a program or process and it's this existential crisis, which I think is a pretty fitting idea for a null, which means the concept of nothing. It means that nothing exists there. In C, it's really just a macro to zero, but effectively, it is a way for us to indicate that things should not be there. So we can, in fact, use that to say, hey, maybe I want to start by setting my address to null in order to go, this means that there's nothing there yet. I don't expect anything there yet. And I can do conditional checks and other kind of safety checking when I want to do things like find Bob's address to see if it's null, right? So what I can say here is now the address of Bob, we'll check instead if Bob address, oh, thank you. So what if instead Bob's address, if Bob's address does not equal null, yeah, then we will give him a printf. I think this should work. But nothing's been working so far, so let's see. Because it might be a fun way for me to teach you new compiler error debugging. Okay. So it didn't print anything because Bob's address is equal to null. And so we can check and make sure that, hey, is there something real in there? Condition checking. Okay. So we know where Megabyte lives. We know where Megabyte lives. We know how to get there. But the next question is he home? Because like you and like me, sometimes I am not home. And if we're trying to track this guy down, we're kind of hoping that he is. How would we check if somebody's home? Knock the doors, right? We want to go into it. So we do have a command for that, and unfortunately I don't have a very pretty one, but this command is called dereference. So we're going to ask glitch to dereference. Everyone, glitch! Boom! And then we're going to have, I'm sorry, it's not pretty. Dr. Connie has a better one. A little star thing that is going to go woo, 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 woo. And I'm going to ask you to do a little spin if you can. I'll spin it for you. Yeah, okay. And that spin is going to push you towards the house. So we're going to go to our house. Boom! And you can unlock the door and check inside. So with these ones, you'd actually go this way and you lift the top.
Oh.
Okay, so use your key, use your thing to check inside. So before you open that paper, we're going to talk a little bit about dereferencing. So what dereferencing actually does in the computer is it reveals the contents of that address. So the same way that the dereference allowed us to open that mailbox, knock on that door, and get inside, it will show me what is actually stored there. So if we go back here, and we take megabytes address as this pointer. Let's say megabytes address points to this number. And now, who is at the house? Print some character is at that address. Now, what did we need to do to open the door? What was the command, everyone? Come on, yell it. Dereference. Boom. So we're going to dereference that. And that means we put the little star in front of it. And then we can put the regular pointer beside it to show the address. And I'm going to hide Bob's address for now. Get rid of you. No one cares, Bob. It's fine. That's wrong. We care. You'll save the day. Oh, something's happened here. Oh, yeah. I made a typo. Did I mean megabytes address? I did. I meant for there to be an S there. Okay. Boom. And so, megabytes address points to some address, this number here, and M, the character that is at that address, is printed on screen for us. So that's the importance of dereferencing. And you're going to end up seeing this a lot as we kind of go forward with coding and get into things like arrays and other kind of functions. Because all of a sudden, we can see at any physical spot where something is and access what it is. All right. So if that's what dereferencing does, just to remind us, pointers tell us where the address is. Dereferencing a pointer tells us who is at the address. Yeah.
Don't want to get too meta, but given that pointers are numbers, 4-byte numbers, whatever it is, that's data as well, which means it has to be stored somewhere, which means that a pointer should have its own pointer,
address.
which means that that pointer must have its own pointer. Where does the recursion stop?
You are getting ahead of us. Give me 1 second. Actually, wait a second. Our Bob, our guardian here. What was in Megabyte's house?
Megabyte isn't here.
Megabyte isn't here. We had a pointer that when we opened it up actually showed us another pointer. And this ends up with this indirect referencing where we can have exactly what you're saying of like pointers have addresses and pointers can point to pointers can point to pointers. And we keep going down this loop and this rabbit hole. And this does happen sometimes. Where does the recursion stop? It doesn't, man. That is why it's really important for you to track these kind of things, like how many dereferencing stars are beside the values that you're accessing, because that will tell you how far you're actually going to look. So for us, we have 1 star. There's a one, we've got a pointer that told us something. So where do we go from here? What's our next address?
0x67.
0x67. So should we check there? Yeah. All right. Let's go. I love it. You guys got me. Okay. You guys got me. But they found him. Okay. So with that, we have pointers. That's the basic concept of it. Addresses to where data is stored in memory and ways that we can then see where that memory is and access what's inside of it. All right, can I get a big round of applause for all of our volunteers? Thank you all so much. How did you like being tradies for the day? Yeah, it was good? Didn't have, we got to stand around with your poles. It's good. Okay, if you guys want to leave your stuff here and grab some Skittles, that would be great. So, in the last little bit of our lecture, because we're coming up to the end of it, we're going to ask the question of going back to that idea of how can we swap variables that exist in a different scope without global variables. The global variables should work. But if we remember that C was passed by value, what if we pass into the function the address of the variable? Do we think that could work? Can we think of any functions that we've been using so far that might actually work on that same principle? That instead of taking in the variable, it takes in the address of a variable? I heard it over here. Anyone else have it? But we're right. Tim, if you'd like to say it louder for the back.
Scanf.
Scanf. If everyone remembers our calls to scanf, we had wondered, what is that ampersand in front of the n? Why are we constantly having to put the ampersand there? It's because scanf is its own function, right? It's its own function that therefore has its own scope and is doing things inside of there. How do we know where to put this variable then? We tell it where that variable should be stored and ask it to put things at that address. Therefore, anyone else with the address of n can walk in and check what's there. And that's how we use that. Okay, so with that in mind, that's our summary. If you know where a variable is in memory and have permission, you can change it. Let's try it with our variable swap. I swear to God, I'm sorry, everyone. We're going to try this one more time. What if instead I don't have my swap taken actual integers? What if instead I have it taken a pointer to an integer? Remember, a pointer is just that variable which stores the address. So it's going to take in a pointer to x and y instead of x and y itself, right? So what does that mean here? It means that instead of actually giving it x and y in the swap function up here, I want to give it the addresses of x and y. Everyone following? Everyone remember why? Because an address and a pointer, the pointer is what stores an address. And so I could do something like this, an int pointer xp that we call the address of x. And I could instead put that in here instead. Or I could just give it straight the address of y. In this case, both are equivalent. Okay, now how do I need to change my swap? Well, I actually need to change it because now it can be pretty simple. If I have an int z, and we're going to, instead of having z be that value, we now need to dereference the pointer. We need z to point to what's inside of that house. And I do that by dereferencing with the star. You're going to see this star a lot. It means a couple different things. I know, it can be confusing. But when you see it in a variable declaration or up top, it means this thing is a pointer. When you see it in assignments like this, it means I'm dereferencing a pointer. Okay, so z is going to hold onto the contents of x. And now the pointer to x, see it's on the left-hand side, it's the pointer to x, is instead going to point to what's in y. On the left-hand side, the pointer x. On the right-hand side, what's in y. Pointer dereferenced. And the pointer of y is now going to hold z, which previously held the contents of x. Make sense? We've done this thing here where we went x has an address, a hexadecimal of 08. Y has an address, a hexadecimal of 10. Now instead, the addresses might remain the same, the bottles, and we're just swapping where we're pointing to with them. Got it? Let's see if it works. And if it works, then I have to legally let you go because I will break code after this. Okay. What the heck did I save that as? That was our swap function. That was our swap code, right? Swap.c. GCC, swap.c, swap pointers. Just so we have a naming convention. I'm missing something. I'm missing a semicolon. I told you I had to mess up something today. Okay, Okay. Swap pointers. So before the swaps happened, X was 5 and Y is 10. And then, oh my gosh, that's right. We gave it addresses. And now the swap after shows the contents are switched. That the pointers, all of them have now moved. The labels have moved over. All right. With that, we're going to end up actually stopping here. But I'm going to leave you with one last thing. I said earlier that idea of you could change it if you have permissions. What happens if you don't have permissions? Segfaults, segmentation faults. It basically means that you have access memory that you are not allowed to touch. In the same way here, permissions just mean where we're allowed to build, where we're allowed to see in our neighborhood. And if we are getting a segfault or a memory error, it means we are trying to move to some other neighborhood we're not allowed to be in. So, thank you everyone for today. Thank you for putting up with all our technical issues and glitches. Next week, Dr. Connie will be back, and he will be picking up with you from the concept of pointer arithmetic. Because as we said today, addresses are just numbers. So we can do arithmetic with them. Thank you, everyone. If you would like some Skittles, I have some more. Feel free to come up for being such a great class today and dealing with all this. We've got some stuff, and I can handle some questions as well.